सर आपका
लास्ट
लैपटॉप लैपटॉप का कैमरा
वो लेफ्ट से चला है. Okay, but how do I know? Are they audible? Laptop you can bring it here, no? Okay, system है, ठीक है. All right, कोई बात नहीं. So okay, we are not using this camera. ये कैमरा यूज करना चाहिए. But anyway, अभी म्यूट में है क्या? म्यूट करिए. Yes. I know my video is on now. You're using this camera?
Yes,
No, David. What we can do, we can go with audio. That's okay. Chalo. Oh, yes. Good. Start. Fan on कर दीजिए. ये बेटा fan on कर दो. पानी एक गिलास दे देना. That's okay. Good. बैठ जाइए आप लोग.
Yes.
ठीक है चलिए. ये जो replace कर दिया आपने. ठीक है. But we'll have those. This has been updated.
Yes.
Very good. चलो slide share करो. So I'm not able to list. Okay, you have already muted all the candidate probably.
Yes.
Okay. Good.
Last we will take.
All right. So just can you all message if I am audible, loud and clear? Yes, great. So sorry for the delay, and we'll get into the second lecture of our course. Just a minute. So what we can do? Okay, am I audible now? Just one can say yes, that's enough for me. Yes, thank you. So today we'll be talking about energy storage devices. And the interesting part of energy storage device is why, first of all, a device is required in electric power systems. Okay. Yeah, good. Thank you. So first of all, why energy device is required become a question to all of us. To my understanding, how the birth of energy storage device took place in the field of power systems. The number one is the intermittency nature of different type of renewable energy sources, number one. And the number two, perhaps whenever a system faces insecure or unreliable energy supply, that case we need storage devices. All of you please try to understand, if the energy supply system is not completely reliable, we need to store energy to get access to electricity around the day. That is one thing. You all know that in early days, we used to use a UPS at home, a small battery, which used to get charged during the daytime. And as and when there is no supply, that UPS actually gets switched on. That is one type of storage device to me. As well as when we have a lot of actually PV and wind to be integrated in any power systems, and they are not constant, and they are not happening around the day, and hence to meet out the electricity for around the day, we need storage devices. So it's very clear. And then you have storage system, hybrid energy storage systems, and then energy storage into grid. Finally, statistics of storage development for both globally and nationally. Now, the moment we talk about purpose of storage devices, as I already told you, once we have majority of energy resources belongs to a variable renewable energy, and then that case, we need to store the energy to cater around the day in a constant magnitude. And as I told you, that intermittency, which is certainly a criteria for any system to have a constant power supply or a flat generation system. And for that, actually, we need to have storage devices. One thing is very popular, that is electrification and decarbonization of end user sectors. To promote intermittency or green energy sector, we need to have storage to make sure that, the generation curve is flat. Excess variable renewable energy can be stored and used in a consistent and controlled manner. All point number 1, 2, 3, 4, they all fall under the same bracket, the same umbrella of intermittency. And then potential solution to increase system flexibility. So this is a very, very important point. For example, when you have excess energy, you will experience actually voltage issues. And when you have less generation, you will have actually under voltage issues. But if I can have a battery, that battery can be used as a load as well as generation. Battery can be used as a load as well as generation. So whenever there are excess energy, I can connect my battery as a load, and whenever there are less energy, I can use my battery as a generation. So that's why we call battery or storage device can be used as a flexible device. Unique capability to quickly observe, hold, and then re-inject electricity, that is anyway true. Very quick charging and discharging cycles can be deployed and scaled close to the location of the need. You can take this device to any location and get it connected. But unfortunately, we have not talked about the limitations and demerit of battery storage system. So probably at this point of time, please concentrate on the merit of storage devices and why do we go for storage devices. Now, this slide is actually quite interesting because we have put a lot of effort to prepare this slide in the past. That is history of energy storage systems. As back as 1839, we had the first storage device, so-called fuel cell, and Sir William Robert Grove, who played a key role in developing fuel cell. Where actually he mixed hydrogen and oxygen in the presence of an electrolyte and produced electricity and water. Then slowly we moved to lead-acid battery. To me, lead-acid battery is really a good one. But there are a few issues and challenges. The number one is about the weight. The number two, it's about the size. If the weight and size would not have been an issue, then probably today all the electric vehicles might have used lead-acid battery as a energy sources for e-vehicles. Only limitation, it's a very robust, very reliable, no maintenance, wonderful. But the only thing actually weight and size is actually pulling this technology back. So French physicist Gaston Planté invented the first practical version of a rechargeable battery based on lead-acid chemistry. Then the third one, which is flywheel energy storage, discovered in the year 1883, and this was due to a military application by John A. Howell, and that is perhaps actually a specific application. It is not too popular, but certainly it's a storage technology which is of importance today. Then slowly the chemistry moved to nickel cadmium battery, 1899. Then we moved to pump hydro storage in 1907. Then we moved to just a minute. Then we moved to 1969 superconducting magnetic energy storage. Then we moved to compressed energy storage in 1978, supercapacitor in 1982, and then the breakthrough appeared in the year 1991 for lithium-ion battery. And finally, the latest technology, 2007 to 10, is about the paper battery. I think, but there is a pause. After 1991, almost everyone in the world started using lithium ion. It has many merits. And the first commercial lithium ion battery was released by Sony. Okay. So if you move to classification of energy storage systems, there are multiple categories. The energy storage devices are of thermal type, which are sensible, latent, and thermochemical energy storage devices. Then we have one more category, which is mechanical energy. Pumps, hydro, gravity, compressed air, and flywheel fall under the umbrella of actually mechanical energy type storage. Then we move to chemical energy, hydrogen energy storage, synthetic, natural gas storage, and solar fuel fall under chemical energy type. Then we can move to electrochemical energy type, where we talk about flow batteries, paper battery, flexible battery. They're all under electrochemical energy storage devices. Now, hybrid energy storage systems. It's a very unique type where we talk about mixed appropriate features of several energy storage systems. For example, I can have a battery system which is partly lead acid and partly lithium ion and partly nickel cadmium. Okay, so we can mix different technologies for overall benefit. Two categories of energy storage systems. Well, why do we mix? That is another question. Because there are two important factors one need to understand. One is power density and the other is actually energy density. So batteries are expected to have a high energy density and high power density, but achieving both is certainly not possible. So what we do, we go for technologies which are reasonably high power density and some technology which are high energy density, and we can have the mixture of these two to make sure that the package is performing much better than a single type. So the categories of energy storage systems, which are either high power, high energy density, and other with high power density, will give you a better efficiency. Combination may be physically and technically limited. Example, when we talk about 1.2 megawatt supercapacitor and battery at United States in 2016. So it's a mixed, okay, we have a supercapacitor and a battery of 1.2 megawatt. Then we have 11.5 megawatt lithium ion and sodium sulfur battery to balance out the frequency fluctuation in Germany in 2018. And then 1 megawatt vanadium flow and lithium ion batteries for net zero target of Monash University in Melbourne, Australia in 2018. So these are the few case studies where they talk about a mixture of two technology for overall efficiency of the network. Now, why do we go for energy storage for energy grid? Now, let's say there is a remote area where we have a house and the village is not electrified. Okay. And if the village is not electrified, then my target is actually just to get electricity. So what I do, Manmohan, basically I put a overall rooftop solar and I get electricity. But in the evening, actually, I don't have anything with me. So I'll put a small battery so that actually evening time also I can run my basic requirements. And day anyway, I'm getting some energy. So that is how actually the target is. But if I put the same solar power connected to a grid, so there are not necessarily for energy requirement, but that may have actually many auxiliary benefits, ancillary service support. So that's what we are going to talk here. When we talk about system operation, battery can help you to carry out the system operation advantage, that is frequency regulation. The moment frequency drops, let's say from 50 to 49.9, I can discharge with a spike, of my battery so that it can be quickly become 50 Hz. All right. That normal power plants and other things cannot do it. So that's what we do have some battery integrated system to make sure that the frequency regulation is being maintained, number one. Then we talk about flexible ramping. As I told you, immediate increase in energy injection. That means the load increase suddenly. So who will match that? Only the battery can match it, or a diesel generator can match it, or a gas generator can match it, but not a hydropower. Hydropower plant also can match it for some extent, but not thermal or nuclear. All right. So flexible ramping, and certainly for black start services, we use battery as a reference. Let's say this is our MNIT Jaipur academic campus. I do have 0.5 megawatt of PV, and the grid is out, 33 kV substation is out for some extent. And then what happens, actually my 0.5 megawatt of solar panels will not give any energy. Okay, because the grid is not there. So how do I do it? Actually, I can, if I do have a battery in the campus, I can make my battery as a reference bus. So the voltage of the battery can be sensed by my inverter, and hence actually I can start generating. So battery also can act as a grid to make sure when the system is islanded from the main grid, then also the renewable energy available in the islanded system can start generating. So that is black start service also can be carried out. So system operation, these are the three merits. And then we have investment deferral. This is a very interesting concept. Energy shifting and capacity investment deferral, transmission and distribution, congestion relief. So here what happens, like I told you this example yesterday also, we have a substation transformer, and the substation transformer is extremely loaded, and that need to be replaced by another substation and necessary transmission distribution corridors to meet the extra load. But my worry is that I do not want to go for a new investment or new device installation. So that case, I can have some local generations to cater so that the load beyond my substation is not going to increase. So that means whenever there is opportunity to me, I'll keep some energy available. So during that peak 1 hour that the substation is going to face can be avoided by discharging these batteries. And this can be carried out by the distribution company itself. So distribution company, instead of purchasing a new substation or substation transformer, they put some small, because let's say the capacity is 100 kVA and the load is going to be 105 kVA. So they will put actually 5 kVA of actually battery instead of replacing, putting another 100 kVA transformer to meet that 5 kVA extra. When it is 20, 30, 40, 50 kVA, they will replace. But the small incremental changes, they will go with some local generation. So this is basically energy shifting and capacity investment deferral. So they defer the investment for the transmission and distribution congestion relief. The capacity of the line is 100 kVA. The line is fully loaded, and now you have a customer who is interested to draw another 5 kVA. So 100 kVA become 105 kVA. Okay, and now the distribution line or the underground cable need to be reinforcement, we call. So you put another underground cable next to that to cater that customer. So instead of doing that, actually locally we supply through a battery system. And then you go to the PV and wind generators where reduce renewable energy curtailments. Because we need not curtail means many times, all of you please try to understand. So if I have a PV park and I do have a customer, all right, and now the customer's requirement has gone down, means I'm experiencing a off-peak hour. So during that off-peak power, the PV energy connected to the system need to be derated because my requirement is not there. So instead of 100, I have to derate to 65 or 70. So I think this is a very, very unfortunate scenario where the renewable energy is available to me, but I'm not going to extract because there is no taker for me. And that is where the battery could have been acted as a load and got charged. So that is one interesting thing. And then capacity farming, then mini grids reduce reliance on diesel generators. Yeah, so I think like local people that I told you about the UPS, either you run a diesel generator or you run your battery, whichever is comfortable to you. But in this country today, we all prefer a diesel generator instead of a battery, though it is not a good decision. But most of the time, we feel it's a cheaper, or maybe I don't know the reason. But certainly, it seems to me the life of a battery is not as long as a diesel generator. Probably diesel generator can go up to 20, 30 years, but the battery can go from 5 to 10 years. So that would be the reason Indian industry always look for a diesel generator instead of a battery. But to me, considering the carbon footprints and the long run sustainability goal, we all have to really prefer to go for batteries instead of diesel generators. Now, looking into system operations provides key services needed for the operation of a system with high share of variable renewable energy. So what we can do, the frequency regulation, which is an important part, fast response typically in milliseconds. We have to quickly, give some energy to make sure the frequency is maintained to 50, then flexible ramping, and then black star services. So these are all possible mostly through a gas turbine or through a battery. Now, investment deferral, how it can help you to not to spend more money for the distribution network owners. One is energy shifting, and the second one is actually congestion relief. So the moment you talk about energy shifting, act as capacity reserve and discharge during peak hours. The battery can be used for charge and discharge. And so instead of having a you see what is happening today, that to maintain the consumers where the load is keep on oscillating, I need to procure the peak energy from the exchange. Okay, but that's not a good optimal solution because only 2 to 3 hours you have to consume full energy, and rest of the time you have to pay because if the peak is 100, off peak is 50. If you procure the power for 100 megawatt, then you have to pay for 100 megawatt throughout the day. All right. So what people do normally, or the distribution companies do, they buy energy for 50, and the peak hours actually they meet with some external sources, and probably the battery can be used to kind of charge and discharge during peak hours. So that is what the strategy most of the distribution companies do adopt today. And that is the only reason I will give you a case study slowly, very soon, where Tata installed a 10 megawatt battery in Delhi just to make sure not to procure maximum power from the exchange. Congestion relief, which is store energy from excess renewable energy. So I can store the energy because, for example, let's say today in Tamil Nadu, we have huge wind potential. So there are n number of power plants, those who generate actually wind energy in Tamil Nadu. But the load center of Tamil Nadu appears, majority of the load is at Chennai. So all the energy which has been generated may not be, might be difficult for Madurai city to consume, and hence all the energy to come to Chennai. But unfortunately, the networks have not been designed for a flow from actually Madurai to Chennai. However, the plan was actually all the energy will go from Chennai to Madurai before 40, 50 years. So today there is a challenge. All the lines are too congested to evacuate those wind energies available during southern Tamil Nadu. So that case, if I put some batteries in the southern Tamil Nadu, probably the excess energy available to me can be stored and discharged for the Madurai city or nearby city, Kanyakumari, for an example, instead of pushing back to Chennai completely. So that is store excess energy from renewable energy if it is available to me, and instantaneous response to variability. Any oscillation, sudden change can be met easily. Now, moving to service provided for VRE generators. So reduce renewable energy curtailment and capacity farming together will have greater penetration of variable renewable energy by farming the output. Let us see some wonderful case studies. Largest solar powered battery. Okay, so this is one of the world's biggest battery storage scheme. What they do basically, almost 132 huge, truck-size batteries are containers basically that you see export container size, close to a truck size. So it is basically, deployed in Florida, the Florida Power and Light Company, located in Manatee, Florida. The capacity is as high as 409 megawatt. Imagine, close to a half a gigawatt. Okay, so 409 megawatt capacity. The investment is close to 2,700 crores, 300 billion, and then 132 storage containers with an area of actually 40 acres. Right. So estimated to eliminate. Almost 1 million tons of carbon dioxide. That is what expected. This is a storyline where we can see that the global cumulative energy storage installations from 2015 to 20. That is the only challenge why we don't spend a lot of money on this. But nevertheless, very soon, India will also see or experience EU storage installations over a period of time. Okay. Yeah, good. So let's understand what is the Indian energy storage scenario. So I'm very happy that in the last moment, Manmohan and Prashant helped me to prepare this slide. As per the NEP 2023 of the Central Electricity Authority CEA, the energy storage capacity requirement is projected to be 411 gigawatt hour. Okay, so close to 175 is from PSP, from storage, and 236 will be from the battery storage. So we are expecting this a huge, because 230 odd gigawatt hour from battery means we are expecting close to 1,000 gigawatt from renewable energy. Am I right? And it's a very ambitious target. So instead of 2030, may it happen around 2045, but certainly it is going to happen for sure. There is no doubt about it. As of March 2024, India installed a battery energy storage system capacity of close to 220 megawatt hour. Just a beginning. And Chhattisgarh, the highest battery energy storage capacity, accounts to 54.8% of the cumulative installed capacity. So it seems to me Chhattisgarh might have storage on installation, right? So further, CA has also projected that by the year 2047, the requirement of the energy storage is expected to increase to as high as actually 2,000 gigawatt hour, and where actually 540 will come from storage and 1,840 gigawatt will come from battery storage. And expecting actually net zero in 2070, But to be very honest, actually, I don't believe in this number because most likely, I mean, net zero is altogether a different ballgame. Next. So 1,000 megawatt Tehri pump storage plant, which is come on. I mean, can you just message? There was a message coming to me. Someone is interested to know. What is that?
Can we get this, please?
Oh yes. It is for you only. Okay. Yeah, but because do you like this diagram or you like the content? I think we will share. Don't worry. So 1,000 megawatt Tehri pump storage plant. The reservoirs created by Tehri and Koteshwar Dam will function as upstream and downstream. And I'm very proud and happy that, perhaps I physically witnessed for last 30 years to this dam actually almost every year or alternate years. We have done a lot of work actually for Tehri Hydro in the past as an advisor, as a consultant in many more levels. So enhance system reliability by meeting the peak load and balancing requirements. Consists of 4 reversal pump turbines units of 250 megawatt each. Expected commissioning of the unit 1 and 2 by March 23. I mean, this is a very old slide basically. So by this time it might have been completed. So there are a few interesting case studies we are going to discuss now. And Tesla 100 megawatt, 129 megawatt hour lithium ion battery installed in Australia, South Australia. And the objective is for frequency regulation. Then we have actually 120 megawatt hour battery storage in Germany, the second one for frequency regulation. 38.4 megawatt, 250 megawatt hour. So all of you please try to understand, don't get confused with this megawatt/megawatt hour, okay? I can have a battery of actually, let's say, 100 megawatt operating for 2 hours will give me 200 megawatt hour, all right? So that is what actually, so don't get confused. For example, in my own lab actually, we have 150 kilowatt hour, which is 75 multiplied by 2, become 150 kilowatt hour. Okay, so we say it is 75 kilowatt slash 150 kilowatt hour battery lithium ion installed in the Department of Humanities of Hydro, something like that. So then we have actually, that is installed in Italy, and this is for actually investment deferral, okay? Different.
Please repeat the statement, megawatt and megawatt hour.
Okay. So what we are saying, because every battery, each and every battery, I can have a battery of, let's say, 100 megawatt and operate it also for 100 megawatt hour. Okay, that is possible. But it is also possible that I can have 100 megawatt battery, am I right? But the total capacity of 200 megawatt hour, that means I do have actually a battery of 200 megawatt bank, but discharging at first hour actually 100 megawatt and second hour another megawatt. So my capacity is 100 megawatt at given hour, but the total capacity is actually 200 megawatt hour. You got my point? So this 90 megawatt is basically the capacity, and 120 megawatt hour is the total energy that can dissipate from the complete energy pack. All right. So the moment I say 90 megawatt and 180 megawatt hour, what does it mean? So 90 megawatt hour 1, another 90 megawatt hour 2. So the both in 2 hours time, total in a day, they can give you, let's say 2 hours time can give you 180 megawatt hour. Okay. So the capacity of the battery, which is in megawatt, multiplied with hour will give you megawatt hour. Okay. Using 100 megawatt battery for 2 hours of operation will give me 200 megawatt hour. Is it okay? So that's what actually the megawatt and megawatt hour or kilowatt and kilowatt hour operation. So then we have actually NGK. Just a minute. Parik, no positive input. Okay. Okay, so then we move to the Japan one, which is 34 megawatt and 204 megawatt hour sodium sulfur battery storage system. And this is for reduced renewable energy curtailment and ancillary services. Then we have next one, which is 1.5 megawatt hour battery plus 270 kilowatt solar PV project. This is in Yap State, and it is used for reduced reliance on diesel generators in mini grids. Low carbon lithium ion battery in Glastonbury, which is 40 megawatt, and Clatter close to 10 megawatt in UK for frequency regulation. And finally, we had 30 megawatt, 120 megawatt hour lithium ion is for California, United States. Okay. Mm. So here again, once again, before I go to the next one, 30 megawatt, 120 megawatt hour. So what we do, that means we have 120, megawatt hour capacity. Means hour one, it is 30 megawatt. Hour two, it is another 30. Hour three, another 30, and hour four, another 30. So the battery, for example, fully charged, assume, so they can discharge 30 megawatt in first hour. They can discharge another 30 in the second hour, third another 30, and fourth another 30. Okay. And if you like to discharge all four at a time, so for 1 hour, I can discharge 120 megawatt. That is what the concept of megawatt and megawatt. So either you take 30, 30, 34 hours, or you take 120 in 1 hour. All right. Good. So these are the quite interesting references I expect all of you to use and try to understand more about, energy storage systems. So, but anyway, so if you see the case of actually energy storage continuation to the previous lectures, classification of energy storage systems, technical characteristic, terminologies, why batteries, what are those applications, different battery technologies, and strength and weakness of different energy storages we'll be discussing in next 30 to 40 minutes. So once again, if energy storage systems are majorly divided into mechanical type, electrochemical type, chemical type, electromagnetic type, thermal type, and hybrid type. And mechanical type, which is pumped hydro compressed air flywheel, and electrochemical, it is lithium ion, lead acid, nickel cadmium, vanadium redox, and sodium sulfur. Chemical, they are fuel cells, hydrogen storage, biofuel, electromagnetic, supercapacitor, superconducting magnetic energy storage, SMES, thermochemical, latent heat, sensible heat. Because that will give an idea. Because if I look on the past students, what is happening? Slide is not changing. Okay, can you see this slide? Very colorful slide. Yes, very good. So, normally, you see, if you have a system, the question comes, how much of battery rating and what time? That is not known to many researchers, or the planners are really confused. For example, even today, if you talk to BSES or even Tata Power, Reliance Power, they all wish to have a battery, but they're not very sure which battery I have to go for. Am I right? So that this characteristic or this diagram will very clearly say, depending upon the magnitude that you need to install and for how many hours. If you have the idea of the hours, because how quickly you like to discharge in an hourly time, or you want to do wrapping in seconds, you like to discharge 100 megawatt. And right, depending on the application, that capacity the battery must have to discharge also. That is not possible with all chemistry. So depending upon your application, depending upon your capacity, depending upon your time of discharge, we need to select the battery type. So for an example, you can just see to that. If you like to discharge a battery in minutes, all right, and the capacity is close to, let's say 300 kilowatt. Can you tell me what are those batteries suitable? I think many battery categories are suitable, but certainly lead acid or lithium ion is certainly seems to be a suitable type. So transmission distribution support grid, minute discharge, 200 to 300 kilowatt or probably megawatt level. I think lithium ion would be an interesting choice. But if you're going for, let's say, 1 gigawatt, bulk power management, in hours it need to be discharged, then to me, it is pumped hydro storage, the last block. So we need to plan what exactly I like to do for what application. So it's a three-dimensional figure. X-axis represents the magnitude. Y talks about the hours of discharge. And another plane on the top which talks about your reserve responses. What about lead-free ceramic-based? Okay, if someone is asking about the specific type of battery, why they're not being included, am I right? Okay, all right. So probably the kind of references we have used in 2017, the diagram which has been taken from actually Moller, and this is in 2017. So these are the concept actually they have considered.
That is having ultra high power density. So maybe for more voltage we can.
Yeah, but this is because once you understand the chemistry of that battery, probably that can go closer to other chemistry type actually. All right, excellent. So electrochemical and electrical energy storage example batteries cover the mid-time range, minutes to hours, and allow scale up to megawatt size. Pumped hydro and compressed air energy storage may reach a gigawatt size. Chemical energy storage as hydrogen has the largest potential for large-scale energy storage. There are few terminologies we already talked about, but again, because people say high power density or high energy density or low energy density. So what is energy density? So for a given volume or a mass, the amount of actually energy that is being stored. So the amount of energy that can be stored in a storage device that has a given volume or mass, okay? So similarly, power density, we talk about the amount of power that can be stored in a storage device with a given volume and mass. Response time, it is the time for an energy storage system to go from 0 to 100% rated power, while rated power divided by the response time is the ramping. Now, what is cycle life? The cycle life for an energy storage system is a function of depth of discharge and is the total number of cycles that an energy storage system can provide at any depth of discharge over its life. That is the cycle. Efficiency, round trip efficiency is the percentage of electricity put into storage storage technologies. So the energy density, which is red means not so good, gray means good, and blue means actually very good. So you can identify different type of actually batteries. So we have taken redox flow, lead acid, lithium ion, supercapacitor, flywheel, with many parameters such as energy density, power density, usable capacity, cycle life, long-term storage, response time, efficiency, maturity, flexibility, safety, and cost. So out of this, please all of you guess, considering those parameters, which battery technology seems to be the best one? Certainly the lithium ion, the center one. Lithium, okay, because there is no reds. Excellent. I think my students are very intelligent. Huh? I think there is no red mark, which is not so good, and hence lithium ion, 10 out of 10. So let's move to the next slide. Oh, this is a suited application where the battery can be used. So I will just try to explain a little bit about a duck curve. You all know it, but still I'd like to repeat it because what happens when the characteristic, the load characteristic when we plot, sometime the load actually drops as low, and then the peak appears through a ramping. So that means within a short duration, all of you please have a look, 2012, 2013, 14, 15, 16, 17 and 2020 load curves are actually plotted. And what is happening for the particular hour actually between 12 to 3, the load actually drops as low as possible. So I will tell you a simple example how it happens. Just ignore this diagram for the timing. Let's say we have a load of actually 100 gigawatt. And this 100 gigawatt is coming from, from two different sources. One from a synchronous generator, and the second it is coming from the solar park. Okay, so 50 megawatt is coming from actually solar. Another 50 is coming from synchronous machine or synchronous generator, and 100 megawatt is my load. Now I'm plotting the synchronous machine characteristic. Let's say how much generation it does. So what will happen? First midnight, let's say I plot from 12 midnight, first hour, 1 a.m. There is no sunny, okay, no sun power, so maybe no PV. So everything comes out from a synchronous generator. That is what you see, it keep on generating. And the consumers maybe not be 100, maybe 70 or 80. So it provides actually, or maybe 20, 30, whatever it is. So that is being catered. But for a particular duration of 7 to 8 hours, now the actually synchronous machine will reduce its generation. It will take maximum from your PV and little bit it will take from the synchronous machine. Maybe 70 is the requirement, 50 from PV during 11 o'clock and 20 from actually synchronous machine. But slowly move, and at 5 p.m., what will happen? Suddenly, you will expect actually all the load must come actually from the synchronous machine, and there is nothing available from the PV path. So what I'm saying, at 4 p.m., the synchronous machine output was actually 5 megawatt, and at 6 p.m., suddenly it is 50. So can my synchronous machine of 50 megawatt move from actually 5 megawatt to 50 megawatt in 2 hours time? That is possible if the ramping capacity is 25 megawatt in 1 hour. Then only I can actually go to 50, okay? I'm giving a very simple example. So it may so happen if it is a big generator of, let's say, 500 megawatt, then it must go from actually 10 to 500 in 2 hours time. And that is the challenge associated with the duck curve. And that is what actually we experience. So having more PV in the system will lead to instability, because my machine, what I'm calling to generate 500 megawatt in 2 hours, which is next to impossible, ramping is not possible, the system will lead to collapse of the unstable region. All right. So what we are thinking under such situation, if my machine is not able to ramp, then my battery storage system must be able to support till the time the machine comes to its full capacity. Okay, so that is what actually so the discharge when the load is higher than the generation, supply critical load during idling, voltage profile improvement network, upgrade deferral, reduction of losses, etc. But certainly, the current scenario having any system with maximum renewable, especially from PV, machines having actually not huge ramping characteristics, need to have batteries to survive. Okay, so supercapacitors, flywheel, lithium ion, lead acid, redox. So all this, they will be very helpful for grid stability and system stability at large. Okay, the system will be more stable if you have renewable integrated power systems with a huge amount of battery can make your system stable, and it will allow your synchronous machine not to reach to its maximum very quickly. But why do we go for batteries? Is there any other thing? So batteries, especially lithium ion, fit best to decentralized application due to their flexibility and ability to store from minutes to multiple hours and from few kilowatt to multiple megawatts. While there is no best technology for all usages, lithium ion currently offers the best set of characteristics for most, and 95% of new storage installations in 2018 rely on lithium ion, excluding pumped hydro. I think pumped hydro is the best one to my choice, but most of the power plants do not have that provision, excluding the Canada where the pump storages are very, very successful. But actually, in most of the cases, actually, the pump storage is not able to have enough energy during off-peak hours to back the water to the top and then start generating. So pumped hydro still makes up approx 90% of storage capacity, but suitable locations are limited. Different battery technologies, all of you please concentrate. We'll take 5 varieties, lithium ion, NAS, flow, nickel cadmium, lead acid. Energy density, as you could see, it is maximum in case of lithium ion, and round trip efficiency is also maximum in lithium ion. Lifespan is also maximum in case of lithium ion, and eco-friendly is lithium ion. It is basically a marketing strategy, but today people are saying there are many more technologies which are much better than lithium ion today. So probably there was a time where flow batteries are considered to be the best, and even nickel cadmium lead acid also considered the best when these technologies were not available. Okay, someone is interested to know a little bit about the pumped hydro storage power plants. Okay, I'll be very happy to explain. Have you visited? I think most of you might have visited a hydropower plant. If not, please plan yourself to make sure that you visit the nearby hydropower projects. So what is happening? We do have a dam, and then we store water, and the dams are sometimes naturally or sometimes being made, and this water need to be pumped to the generator, okay, and then actually we generate electricity. That is what the idea is all about. But the challenge here, the water which has gone to the downstream can again be brought back to the dam using electricity, right? So if I have generated X, megawatt hour of energy through a hydropower plant, and if I would like to take back the similar water back, then I need more than X megawatt hour of energy because of efficiency and other cases. So whatever I've generated, if I like to take this water back to the dam, probably I'm under loss. So no one will do it. Even today, the pumped hydro storage systems for 1 cubic acre, okay, 1 cubic volume of water, if I like to discharge, I spend 1 unit of energy. When I take it back, I have to spend more than 1 unit of energy, considering the efficiency. But why we need to do it? Because let us imagine during peak hours, if the cost of energy is 5 times than off-peak hours, off-peak hour cost is ₹2, peak hour cost is ₹10, then I do not mind spending twice the cost of ₹2, that is ₹4. I'm ready to invest and get the water back so that I can generate when the energy cost is actually ₹10. So with that philosophy, so it is not about the energy efficiency, but it is about the financial benefit or meeting the peak hours load requirement. We always take the water back during off-peak hour. Okay, so whenever we have excess energy available to me during off-peak hours, that excess energy can be used to pump the water back to the dam, and that can be generated during the peak hours. So it is something like you have a load curve or a generation curve. When you have actually generation is more, load is less, I will charge my battery and then discharge actually when my generation is low and load is more, I can discharge. So the battery is acting as a storage. So the pumped hydro storage plant, the mechanism is also similar to a battery, where it takes your energy during off-peak hours, okay, and generate during peak hours. So that is the philosophy. Hope you've understood actually. Is it clear now, the operation of pumped hydro storage power plants? Nobody is. Thank you so much. Okay, very good. Suklaji, samajh mein aa gaya. Very good. Done. Huh? Oh, great. Thank you. So we'll move to the next one, to battery applications. So energy shifting up to approximately 6 hours fast response, grid following or grid forming. So the energy shifting takes place from 1 hour to another. Voltage and frequency regulation, spinning reserve, ramp rate control, transmission distribution upgrade deferral. So could you see this from the graph actually, So we actually observe, the energy during off-peak hours. So we are actually increasing the off-peak, load characteristic by doing some charging. So the blue shape that you see is basically taking the load curve up, increasing the load, and then we supply during the peak by bringing the load characteristic down. So what is happening instead of a huge variation from minimum to maximum, now you could see the please explain frequency regulations, sir. Okay. All right. I'm coming to that. So, so what is happening? Frequency regulation, I'll just give you 30 seconds. So peak saving, you understood. So what we do during the peak hours, we discharge the battery, and during off-peak hours, actually, we charge the battery so that the load curve will be from the main grid. If you see the load or the generation supplied, excluding the battery, will be almost close to flat. Okay, so it is now completely valley and becomes slowly flattened due to the upper portion of the valley actually being catered by the external source like battery. All right, so you can make the load curve flatten by charging your battery during off-peak hours and discharging during peak hours. Now, talking about the frequency regulation, as I told you, because whenever okay, so when we talk about frequency regulation, and sometimes it is 49.95 to 50.05. The frequency, if the frequencies keep on changing, why the frequency changes? You are riding a cycle with a speed of X meter per second. Suddenly your friend jumped into the back seat. Your speed drops, okay? That means the frequency drops. Means when you have a huge load to be catered at a particular point as a load, when you increase the load suddenly, then actually the frequency is expected to drop. And that we do not want that to happen. So how we can do? So your friend whose speed got reduced from 5 to 3 meter per second because of another friend jumped into the back seat, your friend has to cycle faster. Am I right? To become actually again 5 to 6 meter per second speed. So, and that source will come immediately through the battery. So we say the frequency regulation can be managed by additional source such as batteries, which can be used to discharge during increase in sudden load, okay, or any increase or load changes. Whenever there is a load change, increase in load change, your battery can immediately discharge to maintain the frequency constant or desired variable. Good. So I think this all about today's lecture. You can go through those following references. And I mean, these are the references that you can see. And finally, yesterday some of you asked me for some textbooks, okay? So my friend Manmohan, prepared a list of textbooks that is affordable. I will not say affordable, but I will say they're good books. Fifth one is quite affordable. Okay, this is
5-6.
Wiley, yeah? Okay.
It's Indian adoption.
Japanese also, but actually Indian adoption. So I think some of you, I mean, the books you can just refer, which can be affordable if you can get access to some online materials from your library of your institution is okay. Or if you can afford to get an access to some costly textbooks available in your library is fine. Or if you have to buy your own, then you can see what best you can manage. So with this note, actually, we come to an end for today's lecture. If you have any doubt, I'll be happy to respond. Thank you very much. Over to you.
Thank you very much. If there is any query, please let us know. You all of you are panelists. You can unmute yourself and ask any query if you have.
No question? Oh my God.
Good evening, Sir.
At least two questions.
Okay, sir. Now, what will be the overall efficiency when we use this
Please,
pump
can you
motor?
introduce a little bit?
One by one. One by one.
Yeah, sir.
Please introduce yourself.
Myself, Chandrasekhar, yes, from Bangalore University, from Bangalore, sir.
Okay, Dr. Chandrasekhar, go ahead.
No, sir, yet to become a doctor, sir.
Okay,
In
okay,
future.
okay. No worry, Mr. Chandrasekhar.
Yeah, that's better. Sir, overall, what will be the efficiency of this system when we use the pumped motor? How much percentage it will improve?
No. The efficiency is as high as actually 85 to 90%. You need not worry about that. But normally, if let's say even efficiency is 100%. But why do I do it? What benefit I will get? Let's say I have spent, generated X unit of power. And if I have to use X unit of power to get the same water back, so it is like, the plant is running the same way, no benefit. Am I right? Only if the discharge cycle is during peak hours and reverse water will be during off-peak hours, then the cheaper energy will be used to take the water back and generate during the costly hours. That is the philosophy. Or kuch nahi, that's all.
Okay, thanks a lot, sir.
It is something like buying a ice cream for 50% discount, then in the beach and eating during the next day sunny hours. Got it, Chandrasekhar?
Yes, sir. Yes, sir. Yes, sir.
Thank you. One more question we can take up.
Hello, this is Rajendra Singh from Gujarat.
Yeah, please go ahead.
Yes, sir, I have two questions. One is, sir, this battery, as we are targeting very high capacity to support that peak load. Since the lithium ion is a very rare material in India, so what is our plan to for a self-sufficient this? And also, actually, I have heard some paper or some research like that, even though the total carbon footprint over the year will be less, but there is a huge carbon footprint at the initial development of those batteries.
Very good, very good. So I will answer the second question and then quickly go to the first question. You have both the questions asked, no? Or you have one more question?
Yes, sir, both the questions.
Very good, very good. So first of all, it is true. So we go for lithium ion battery, for an example, and the carbonization happens in the process of manufacturing battery. Okay, and what we compensate in the due course of time is not significant. That is true. I mean, we all agree. Until unless the batteries are manufactured by a clean energy, we cannot say we have truly reduced the carbon footprint by going through batteries. If I use a thermal power plant to manufacture a battery, lithium ion, and then use that lithium ion for green power collaboration and claim that actually carbon footprint is reduced is not really correct. So for that, before we strongly comment, we have to calculate how much of carbon footprint we create by manufacturing a 1 megawatt of lithium ion. And then we conclude what is the carbon footprint we have saved through 1 megawatt of or 1 kilowatt of actually lithium ion, how much we created and how much you have saved. If the difference is not significant, probably your argument is correct. But by simply saying that it is not completely useful in terms of carbon footprint is not correct. So certainly it is a good idea to have renewable energy to be used for manufacturing batteries, but which is realistically not possible. But to my understanding, what literature I have studied, we create carbon footprints for manufacturing green batteries, but nevertheless, it is not exactly equal. We get some benefit, but the benefit can be, extended to a next level if the manufacturing is also being carried out through non-thermal power plants. That is one. And then moving to the first question, can you just repeat the first question?
Sir, this is regarding that our self-sufficiency on manufacturing.
Got it. Okay. You see, I mean, that's why we are not aggressive in our battery installation today. Because if you would have our own technology, like US and China, we could have also gone for gigawatt level battery storage technologies now. We are not doing it because we do not have our own technology. It is very expensive. We cannot afford to do it. But to me, India must, my recommendation, personal recommendation, India must explore maximum pump storage power plant in this country and hence go for actually storage exploration. Thank you.
Yeah, that's correct. Thank you, sir.
I think one more question was from Miss Vaha. Would you like to ask? Last question we are taking. Earlier you have unmuted. Miss Vaha Khan, any questions from your side? Previously you had unmuted. I think no more.
Okay, but what we can, I like to conclude today, all of you, without keeping all the material to be reviewed during end of the course, please revise from time to time. It is very, very user-friendly content. So you most likely will understand everything, but please spend some time to read in the evening hour. With this note, thank you very much, dear friends. Bye-bye. Okay.
Thank you.